So I want to take this AAA battery and I want to determine how much energy is stored in it. And I can do that by draining it. And I, in fact, want to do two things. And two things I already did. I'm going to show you how to analyze it, though. I want to drain the battery and record the voltage across the battery and the current coming out of the battery. And then I also want to measure the internal resistance of the battery and see if that changes. So if I take a real battery like this, I can't get any amount of current out of there. And we can model this limitation of the battery by assuming there's a perfect voltage source inside and an internal resistance. And that all is inside of it. And that's what we call the internal resistance. So as the current draw gets larger and larger, then the voltage drop, there's an extra voltage drop across the internal resistor, and you get less current and the voltage drops across the battery. So that's one way. That's why you can't get an infinite current out of this. Or it's a 1.5 volt battery. If I hook up a 1 ohm resistor, I'm not going to get 1 amp out of that. Okay, 1.5 amps. So let's first look at the energy, and then we'll come back to the internal resistance. So let's say let's just call this V battery. It's the voltage across the battery, and then I have I, the current coming out of the battery. And I used Logger Pro and Vernier sensors to do this, so it collect data every 30 seconds. I think I did 30 seconds. So the power of the battery, power is I delta V battery, right? That's delta V technically. So if I multiply the current times the voltage of the battery, it gives me the power it produces, which is the time rate of change of energy. We define power that. So if this is in amps, that's in volts, this would be in watts. And then if that's in seconds, the energy would be in joules. Of course, as I drain this, both of these can change. So let's just say I get some power curve like this. So here's time, power, and it decreases. I don't know what it does. Maybe it increases. Who cares? So if I solve this for delta E, I get P delta T, but that assumes that the power is constant, which it's not. So what we do is we're going to have to do a numerical integral of this. Imagine that this is actually a whole bunch of data points. Actually, I should spread them out. Like that. These are the power data points at different times. If I have that and they're not evenly spaced because I'm a terrible drawer, but what are you going to do about that, huh? You can't. You could practice drawing, but so if I think about each of these little blocks of delta T, then I can calculate the power as the change in energy is the area of one of these rectangles. And so I have a whole bunch of different rectangles. I'm drawing these from the back side, but you could do it either way. That's just the way I did it before. So each of these has an energy delta E, which is just going to be P as a function of T, or whatever it is, times delta T, right? So that's an easy thing to calculate the area of that square. Then the total energy is just going to be adding up the sum of all these boxes. That's what we do in integration anyway, and we're going to do it with data. And I'm going to show you how to do that in Python. We can also do that with a spreadsheet, even though I just don't really like doing the spreadsheets. Okay, now what about this internal resistance right here? So let's use the loop rule for this. If I do that, I have V0 minus IR internal is equal to V battery, delta V battery, right? I don't really care about the load. I do not care about the load at all. I care about the current. So if I know the voltage inside of here, which what I would get if I just measure the voltage across that without any load on it, then I can calculate I internal if I know the current voltage of the battery. Now, here I am going to get into this problem. I just realized I'm not even going to do this because I think that the voltage across the battery changes with time, the V0. So I'd have to actually disconnect the circuit to measure that. But if I did measure that, and I measure the current and I measure that, I could solve for R internal. So I'm not going to do that now. Not going to do that. Maybe I'll do another experiment later. Let's just calculate the power in the resistor. Okay, so we have a bunch of work to do. So let me show you the data. And I'm going to, this is my spreadsheet of the data. Okay, so this is the data that I collected. I copied it and pasted it from Logger Pro. Oh no, that's not the one I want. I want this one. I did it twice. Here's run 2. And so you see I got negative current, negative voltage because I made a mistake in hooking it up, but it's still fine. And I'll give you a link to this, and you should be able to look at it if you want to. So the first thing I want to do is to get this to Python. And I'm using GlowScript v Python, which means that I don't have a lot of the modules that you could normally use, and that makes it a little bit more difficult. But I have a little workaround. So I'm going to copy all this data. There's a lot of it. Oops, that's too much. So I'm going to copy the time. Oops, not that. Well, that's fine. Copy that whole thing. Now I want to paste that into my Python program as a list of data, but it doesn't work because it doesn't have all the commas in there, and it looked really weird. So let's fix that with a text editor. So if I have this text editor and I paste my data right there, I'm going to go up here and delete that first time because I don't want that. And now I'm just going to find and replace. So I'm going to find all of the carriage returns, which I did by just highlighting the carriage returns and paste it in there, and replace those with commas. So I'm going to replace the returns with a comma and replace all. And then I get that. Now I can copy this and go to my spreadsheet, my Python program, and paste that in. So, this may not work for you. This doesn't work for everything. Okay, and I already did that. So I pasted it in. So that's my time values. I did that for my current values, which doesn't work. And I did that for the voltage values. So that's what I have for all those. Let's just make a graph of voltage versus time so you can see how that would work. So let's make a graph. G1 equals graph. Make this a little bit bigger. I'll give it an X title. Let's plot voltage versus time. So X title is going to be time in seconds. The Y title is going to be equal to V, the voltage, VB in volts. And then I'm going to do this. Width equals 500. 500. Height equals 250. That might still be too big. And then F1 equals G curve. Color equals color.blue. And now I need to plot it. So I need to go through that list and access each one of those things. Let me make a simple list so you can see how to do lists. If you haven't dealt with lists in Python, this will be useful. So let's call this TT. It's a list. I'm going to make some numbers in here: 0, 0.5, 1, 1.5, 2. And then VV is my list of voltages. It's going to be, let's say, 0, 2, 2.3, 3.3. How many do I have? I have 1, 2, 3, 4, 5. 1, 2, 3, 4. I need one more. 3.8. Okay, so I want to plot this. But first, if I just do this, print TT0. That'll print the first element in that list, so it should print 0. TT1 is the next element. But what I want to do is to go through each element in the list. Now, I could do this. I could do a cool loop like this for what should I call it? TA. I'm just making up stuff. TA in TT. This will go through each element in the list and call it TA. And then I can print TA. So it will print out all those values. And so it did, right? But I'm going to do something else. Watch this. For this one's super useful. I, in range, the length of TT, print I. So this will just go through 0, 1, 2, 3, 4, the index of each item in there. And it doesn't print out the numbers, it prints out the index, 0, 1, 2, 3, 4. But now I can use that index to print out the times. So I get TTI. So TTI will be 0, then 0.5, then 1, then 1.5, then 2. And that's important because then I can use that same index in the VV list. Right? So let's just print them both out. print VVI. So that will use the same index for the voltage list, and I can print those out too. Okay, so we're going to do the same thing with a much bigger list to print the voltage as a function of time. I'm going to do this. For I in range. So range makes a list of indices starting at some number up to some number by step size. And so if you don't say what the start is, it starts at 0. If you don't say the step size, it uses 1. So that's why I'm just doing the length of t is that many, how many things are in that, and it'll go through each indices. So then I want to do, I can do this in one line. F1.plot. Did I use a capital V? I did. I want the horizontal component to be ti, and the vertical component to be vi. And that's it. And there's my voltage as a function of time. Of course, it's negative. I can fix that just by going right here and say negative. And so then one of the things I did, which was I think kind of nice, is that I collected data on the voltage without connecting the wire first. So I have the voltage without any load on it to start off with, and that's going to be useful later. And I did that at the end too. Okay, but that's how I make a graph. Now what I want to do is to plot power as a function of time. So we have to actually calculate the power. So I can do this all in one step. Let's say power is an empty list. And then I'm going to add an item to the list. I'm going to say power equals power plus I times V, right? So it's just going to be II times VI. And since they're both negative, I don't have to multiply that by a negative sign. And then I'm going to plot PI as a function of time. I can do it all in one loop. And then I guess I should change this to power in watts. Power in watts. Okay, so then you see here, there was no power because I didn't have it connected up. And then it jumped up, and then the power output decreased over time until it got close to 0, but not exactly. So now what I want to do is to calculate the total energy. So let's do that. We're going to go through that list, and we're going to integrate. And I'm actually going to go through not the whole list. I'm going to skip the first element, right? Because if I think of these as a bunch of points, I need 2 points to make a rectangle. So I'm not going to start with that first one. I'm going to start the second one and use the difference between the time difference between that and the previous one. So let's say this, E equals 0. I'm going to calculate the energy for each piece and then add it to this. But that means I need to start with some known energy. So that's my known energy, 0. Now I can go through the whole list. Not the whole list. Watch this. For I in range, I'm going to start at 0. No. Yeah, let's start at 0. Length of t minus 1. So I'm not going to go through the whole list. I'm going to start at 0 and go to the end, which was kind of dumb. I should have done, I feel like I should have done, I should have done, if I do 1 to, let's do that. Let's start at 1 and go up to this. So I'm going to start 1. That way I'll be able to look back. Now I can calculate the DE for that little time step. DE is going to be equal to the power, which is PI, and it's not the first one, right? And then I need to multiply it by the width of that step. How much time was that? They're all the same, but I'm going to do it anyway. I'm going to say this is TI minus TI minus 1. Right? That's my delta T right there. And then I'm going to add that to my total energy, E equals E plus DE. And then that should do it. And then I can say print E equals E joules. And I get 0.397 joules. Now, I know that the batteries have about 1,200 milliamps. So let's see, a milliamp They're 1200 milliamp hours. So I need to convert this to joules. Let's convert 1200 milliamp hours to joules. So let's say EBR for rated battery energy is 1200 and milliamp hours. So how do I calculate that in terms of joules? Well, this is the current times the time. Milliamp hours. So that says you can run 1200 milliamps for 1 hour, and that would be your energy. But you didn't multiply by the voltage. So I think they use a nominal voltage of 1.5 volts. So if I multiply 1.5 volts times 1200 or 1.2 milliamps, that will give me the power. And then if that's in watt, that would be in watt hours. And then I need to convert the hours to seconds. So I'm doing this, I should do this on paper. Let's do this on paper. Because I think it's just a little too much. Okay. So here I have E equals 1200 milliamp hours. So this is going to be equal to 1.2 amp hours. And that's not really the best unit because that's not units of energy. But if I know that the voltage of the battery is 1.5 volts, then this energy is actually going to be equal to 1.5 volts times 1.2 amps times 1 hour. And that is not the right units. All I need to do is convert, this will be volts times amps will give me watts. I just need to convert this to seconds. So that's going to be equal to, there's 3,600 seconds in 1 hour. It seems like a lot of energy. So 1 hour. And I got what? I got 0.39 joules. Something happened that was not good. 0.8 watts. Oh, you know what? I think my time is wrong. My time over here, this is in, that's not seconds. That has to be hours, right? 0.8, that has to be hours. So let's multiply this times 3,600 to get it in seconds. And then up here, I'm going to plot this times 3,600. Okay. Okay, so that's much better. Okay, so then over here, I can take my actual energy, let's say print E listed, and that's going to be equal to EBR times 1.5 times 3,600 joules. I think that's right. That says, okay, so it's still not working correctly. Let's do this. 1,200 milliamp hours in joules. Maybe I just did that. So 1,200, 1.5, calculate. Watt hours. So multiply that by 3,600. So 1.8 times 3,600. I keep doing the wrong one. That's going to be another video. Don't worry about that. I think that's right. But that says 6 million joules. I kind of feel like this is milliamp hours. So 1.2 amp hours times 1.5. Oh, I didn't divide this by 1,000. Because I did that in amp hours. Okay, so we don't agree still. And that, I think that's okay. But we're at least on the same order of magnitude. But that's how you would calculate the numerically integrate that data. Let's do the same thing in the spreadsheet. So this one I actually copied. Let's copy this whole thing. And I actually need to open a new sheet because I was logged in as another person, my other person. So here's the empty Google Sheet. I'm going to paste that. Paste it. It didn't paste. There it is. Okay. So the first thing I'm going to do is calculate the power. So P is going to be equal to the current times the battery voltage. That's that. And then I'm just going to drag down a couple cells. I can do some more later. And then I'm going to say DE is going to be, I'm skipping that first one. It's going to be this power times this time minus that time. And then, yes, let's fill that whole thing in. Let's see if this one fills. No, I need to fill these in. Oh, see, this is why I don't like spreadsheets. Let's see if I come up here, fill. Do it. No, it didn't autofill. Okay, let's just see if we can fill this in. And note the number. Okay, so we're at 126. So now I can calculate the total energy. E equals the sum. Is sum 1? Let's see. Sum of, let's say, E, oops. Oh, equals sum. And then it's going to be E3 to E, what was it, 126? What did I say it was? No, don't do that. That didn't work. Equals sum. And let's just highlight these. Oh, I colon, that's what it was. See, this is why I don't like, I told you, I already said I don't like spreadsheets. Okay, return. And I get 0.3965. Oh, but again, that's in, I need to multiply that, that's in units of, that says seconds, but it's not seconds. That's actually hours. So I need to multiply this by 3,600. And then I get that's the same thing, right? 1427. Yeah, same thing. Okay, so you get the same thing. I like doing the Python way because it's easier to make a graph. It makes prettier graphs. You don't have to drag down those cells and stuff like that. I'm still kind of concerned about the total energy listed. I think I'm making a unit conversion problem, but I really wanted to show you an example of how to do numerical integration, so I hope that helps.